Hello everyone, my name is Wei Pan, and welcome to the presentation of online optimization with feedback delay at nonlinear switching cost. First, let me introduce some background information on online optimization. Consider such a problem setting where an online learner have an action space F and an initial point Y0 to start with. And in the first round, the online learner observes a hidden cost function F1, and then he picks an action Y1 that incurs a hidden cost F1 Y1. Besides the hidden cost, he should also pay a switching cost to move from Y0 to Y1, that is C Y1 Y0. This switching cost can be L2DOM or in other forms. And we move to the next round. The online learner observes a new hidden cost function, that is F2, and then he picks an action Y2 and incurs a hidden cost of F2 Y2. And he also pays the switching cost C Y2 Y1. And in round 3, similarly, he observes hidden cost F3 and picks action Y3 and pays F3 Y3 and C Y3 Y2. And the owner just repeat such process. This problem setting is called smooth online convex optimization, aka SOCO. In the SOCO setting, the learner repeatedly observes the hidden cost function and picks an action and then pays the hidden cost and the switching cost. The final goal is to find an algorithm, an online algorithm, which minimizes the total cost as the sum of the hidden cost and the switching cost. Here, we use competitive ratio as the performance metric to measure the algorithms. It is the worst case ratio of the cost incurred by the online algorithm to the cost of the offline optimal. Here, competitive ratio is a better metric compared with the rate, which competes against the best fixed action in hindsight. Because in this setting, the optimal policy is nonlinear and time varying, so the best fixed action in hindsight could be arbitrarily worse than the true offline optimal. We can look at SOCO and one of its variations, OCO with structured memory. We can see that in SOCO and its variations, the memory can be one step or multi-step. The hidden cost function can be revealed before the action or after the action, and the switching cost can be in L2DOM or in Bergman divergence, and so on. And people have come up with algorithms like RBD, optimistic RBD, and so on to achieve constant competitive ratio on these problems. Moreover, there exists some class of online control problems that can be converted into SOCO and its variations. But for now, let's consider a new problem setting. We also have an action space F, and in each round, we assume the previous actions are YT minus 1, YT minus 2, and so on. This time, the online learner observes a location family of possible hidden cost functions. Instead of the exact hidden cost function, we can see the hidden cost is parameterized by a minimizer. It could be the curve on the left, it could be the curve on the right or somewhere else. But what is known is the geometry HT, that is the shape of the hidden cost function. And at time t, the online learner picks an action YT and incurs a hidden cost FTYT. Here, FT is the real hidden cost function. It equals to HTYT minus VT. And VT is its minimizer and determines its location. However, this minimizer VT is not revealed until time t plus k. And this is where the delay of k comes from. It is partial information, a feedback delay on the hidden cost function. And moreover, the switching cost not only depends on YT minus 1, but is a function of from YT to YT minus P. We call P the length of its memory. And in the SOCO setting, P equals to 1. And in our setting of online optimization, with feedback delay and nonlinear switching costs, the learner repeatedly observes the delayed information of hidden cost function and picks an action and then pays hidden cost and switching cost. Here, HT is the geometry of the hidden cost function, and its minimizer is at 0 for convenience. The switching cost is a function of previous actions, yt, yt minus 1, yt minus p, and can be nonlinear. In this work, we use this form of switching cost. It is a function where delta is not specified. If it is linear, then the cost is similar to that in SOCO or OCO with structured memory, but it can be nonlinear. It can be non-convex. So now we can compare the problem setting in this work with the previous problems. It has multi-step memory, it has a multi-step delay, and the switching cost is nonlinear. And we will later introduce our algorithm, IRBD, and we will also show its applications to control problems. And we can look at one example of the online optimization with feedback delay and nonlinear switching cost. This is a drum tracking problem. Yt is the real-time speed of the drum to decide in each run, and ytd is the desired speed it is tracking, and it is sent from a server or a computer. The G involves the gravity and other external factors like the aerodynamic drag. The total cost consists of the hidden cost, say the L2 norm or the difference between the real and the desired speed, and the switching cost to change the speed from yt minus 1 to yt. We see the switching cost has nonlinear term G in the norm. In real practice, due to the communication delay, the drum cannot get the desired speed to track in time. It would get the desired speed ytd from the server at time t plus k, and at time t, it only knows the desired speed as recent as yt minus kd. So it's just to properly illustrate the setting of online optimization with feedback delay. That is a delay on ytd and the nonlinear switching cost. You can see G is nonlinear. And before our problem setting, researchers have come up with algorithms to address the original SOCO problem. RBD regularized online balanced descent, as shown in this page, is such an online algorithm. Actually, it is one of the optimal algorithms for SOCO. It achieves a constant dimension-free competitive ratio. However, it cannot handle a delay in the hidden cost function. We can see from the pseudocode that it needs exact ft at time t. But hopefully, we propose our algorithm, which works for the new problem setting of online optimization with feedback delay and nonlinear switching cost. So let's talk about the main theorem. It says the competitive ratio of our algorithm, IRBD, is big O L plus 2p square L squared to the power of k in delay k. Here, L is the hidden cost smoothness, the P is the memory length, and the capital L is the Lipschitz constant of the switching cost. And we can see this bound is exponential in k. And this bound does not depend on the time horizon t or the dimension d. It only depends on the delay, the memory structure, the convexity and smoothness of the hidden cost functions, and the parameter lambda the algorithm chooses. This means that IRBD is constantly competitive for online optimization with feedback delay and nonlinear switching costs. People would ask, can we improve the exponential dependence on k? The answer is no. We have shown a lower bound, also exponential in k. This means the exponential dependence is fundamental and emphasizes how the difficulty grows as the length of delay increases. So let's look a little further into some details of the algorithm. First, we consider the case when the delay is k. delay k is 1. That is, at each time t, the learner observes ht and vt minus 1, but not vt. Since the latest exact minimizer the learner observes is vt minus 1, he will load the exact hidden cost function of time t minus 1, that is ft minus 1. Then, with exact ft minus 1, he can work out the decision of ROBD at time t minus 1, as if there was no delay. Here, we get a sequence hat y0 to hat yt minus 1. That is the trajectory of ROBD from time 0 to time t minus 1. Then we can optimistically guess Vt as tilde Vt. We can see this guess is based on the ROBD trajectory. In other words, the algorithm is tracking the ROBD trajectory. Then with the guess tilde Vt, we can get a guess on the hidden cost, say tilde Ft. And using ROBD, we can get the decision Yt. Then how about longer delay, like k equals to 2? When k equals to 2, the online learner observes a delayed cost function ft minus 2, and then he can recover the ROBD trajectory to time t minus 2. Since the trajectory is only to time t minus 2, we can guess as far as tilde t vt minus 1, and we can see this guess is based on this trajectory. And we guess as what we do when k equals to 1. And we can use ROBD and tilde vt minus 1 to guess tilde yt minus 1. And this is not done yet. We haven't get yt. So we add the guessed tilde yt minus 1 to the trajectory we use. Now the trajectory is up to time t minus 1. So we can use this trajectory to guess tilde vt. We can see this guess is based on the updated trajectory. And with tilde vt and ROBD, we can decide the decision, the action yt. And this is the case of two-step delay. We can repeat such a process for longer delay, like for the online optimization with the general feedback delay k. We first observe ft minus k and recover the ROBD trajectory to time t minus k, and then we iteratively guess the optimistic v and add the guess of tilde y to the trajectory until tilde yt minus 1. And then we can use the trajectory and ROBD to guess tilde vt and pick the action yt. This is how ROBD works. Then we will look at the applications in online control. We will show the connection of our problem setting to two classes of online control problems. The first one is the linear dynamics with adversarial disturbances. In the dynamics, xt plus 1 equals to axt plus but plus wt. Here, xt is the system state, ut is the action, and wt is the noise. It could be an adversarial disturbance, and the goal is to minimize the squared cost. We have shown how to convert this problem into an instance of OCO with delay and memory. It can thus be solved by our algorithm IRBD. And note that the delay is dependent on the structure of the canonical matrix pair A and B. And another class of online control is nonlinear dynamics with delay and time-varying costs. Similarly, xt is the state, ut is the action, but in the dynamics, there is also a nonlinear term, gxt. This can be more easily converted into online optimization with nonlinear switching costs. The hidden cost is FTYT, and the switching cost can be obtained just from the dynamics. If there is a feedback delay in the original problem on FT, like the drone tracking problem mentioned before, the converted online optimization will also have a feedback delay. This can be also tackled by our algorithm IRBD. So both of the two classes of online control problems will then have a constant competitive algorithm. To conclude, we propose a new setting of online optimization with delay and memory, and the solution cost can be nonlinear. And we propose a new algorithm, iterative RBD or IRBD, and its competitive ratio has a tight upper bound, exponential in the feedback delay K, and it's the first to analyze such an impact of feedback delay in SOCO. And we also introduce applications to online control problems, like the linear dynamic system with disturbances. And that's all for my presentation. Thank you for listening.